knows that this is the tail. Biology is like, I swear. Please, just like tell us what's different and then we get it. Like, you don't have to explain how an ester is made. Like, we know. Thank you.
How is this?
All right then.
Do we have this?
No. It'll be.
Good one. Once again. Thank you.
Thank you.
I'll check if I have steam to grade myself, or will you make Friday?
Yes.
Okay. No. Oh, it's a favorite. Your favorite part of the class?
Kinda.
How can I need to match your expectations. What are you doing this way?
Just take it.
One of your classmates was giving me the work. I was pulling hand on it. No. There is just a lot of materials that it would match better the Friday class. And I want to release you from this one so that you do not think about it anymore. So, this is done. So here is your sign up list, right? And Alyssa plans to do something in this range, something very specific, individual.
We'll see. If I can't figure it out by tonight, I'm just gonna fix something.
Okay, you still have like 6 hours. So just try to identify and on the labs we will be a mix of traditional when I mumble something in front and individual one-to-one sitting and discussing. So I think it reflects what you were choosing. Okay, so last time we were practicing things related to harmonic oscillator in the matrix form. We do have equation and annihilation operators, and we do have Hamiltonian. Right now, I want to be confident. I hope that you are also confident with all other operators based on your homework. But right now, just there is no time to look at it. So the goal is to repeat our steps that we did for particle in the box to solve for non-equilibrium initial state when the system is neither in ground nor in excited but in a superposition. This is important, typical. This is a situation that gives fun results on both experiment and theory, and it is not as boring as static things. So all questions will be answered on Friday, or almost all questions. Today is a little bit of mathematical exercise which gives a new tool that will help to predict the future of harmonic oscillator, predict the time evolution of non-equilibrium state, which is a superposition of more than one eigenstate. So the tool that we are going to cover today is eigenstates of annihilation operator. As soon as we complete this exercise, we will be able to reproduce the result that you completed in last week lab, and some about half of you have submitted the lab report. You remember that if you set either non-zero momentum or non-zero position of both, then the initial Gaussian state oscillates forward and back. Oscillator oscillates, no wonder. And even if you do not assign position of momentum, but the width deviates from the one corresponding to ground state, then the width starts to oscillate with double frequency. So it's kind of major properties of oscillator from dynamic point of view. We are going to reproduce it by pen and paper or by finger and touch screen, whatever, on Friday. And right now, to achieve this goal, we need the eigenstates of the annihilation operator. So since we are in the basis of eigenstates, our any quantum state of oscillator is a superposition of eigenstates with unknown coefficients. And since we are solving the problem of eigenstate, we are acting on the left with operator, on the right it should reproduce the same vector but with the constant. So the goal is to find this progression of C sub n and the value of E. Last thing we did before this, and probably the exercise that you are looking at in your accomplished homework, is the matrix or Dirac form of several operators related to harmonic oscillator. If it is annihilation, it projects, it changes eigenstate number k to eigenstate number k minus 1. And for normalization, it also multiplies by a factor. And this is a progression for each possible state. So the goal that we are going to accomplish is to replace this operator in a single box and do some middle algebra. I pretend that I listen to myself from your side. It sounds cool. Sounds too abstract. What do you expect? Like fireworks, cakes. But what do you expect from this problem? What should after solving, what should come out and how it should help to find oscillating oscillator?
This give us kind of like about the wave with like seemingly no motion.
Yes. Yes. Well, in the lab, we didn't care about eigenstates at all. We did everything in coordinate representation, which is numerically not efficient, but it is very simple to perceive for human. Here we are trying to approach this problem from the point of view of eigenstate expansion, where eigenstates are known. And there is an expectation that after all these coefficients are known, and all eigenstates are known, if we perform the summation, we will get a function that will shape Gaussian. By constructing together all eigenstates, it may get to something more pretty. Your instructor is always talking about dynamics, which means dependence on time. Where's time here? How this equation that doesn't have time explicitly may help to get any time dependence. Where's the Do not hesitate, student. So, okay, now I see a little connection. It's a little less boring. We're still not very high on the scale. You do remember third way to predict future, right? You take state at any point of time as eigenstate multiplied by expansion coefficient, and the third factor eigenfunction, expansion coefficient, and starts with letter E. Two things starting with letter E. Okay, three words starting with letter E. Okay, 4 letters starting with letter E. 4E. Evolution, a occurring through x evolution, occurring through exponential, with eigenstate energy appearing in the power of exponential. So phase accumulation. Okay? So each eigenstate is multiplied by this Euler imaginary exponential, which accumulates phase. And as soon as we solve this equation, we will find it. Right now, it's, so to say, eigenstates at time 0. But then we know that each eigenstate accumulates phase with its own energy. And as soon as we multiply it by exponentials, it will start dancing for us. Okay? I was trying to condense in previous year. This slide was for the whole lecture. I don't know if I fail to deliver it in one slide, next year I need to spread it over the lecture. So we did plug in the operator in front of eigenstates. So this the stop line is eigenstate problem for the annihilation operator. So the summation can be moved front, and then we do observe that bra and ket meet each other, right? When bra and ket meet each other, we practice which property? Orthogonality, normal, yes. So the bra times ket will be either 0 or 1, depending on coincidence or not coincidence of the bracket indexing inside bracket. Now, what do we see? There is two summations, and there is one delta function. So, in some sense, one operator is removed, and it will be wave function is this number that we need from the summation. So, what happens if the summation meets a delta function? Yes. So we cancel each other, and we will have one summation less and no delta function. But as a price, we will need to replace k to the n, or n to the k. We need to just there is one index less. So we replace n to the k in here. In some sense, and just different indices. In some sense, the problem is solved. It doesn't look beautiful, and we need to tie the loose ends, but everything is already here. Right now, we do have two summations on the left and right, and two summations, and the nature of the basis function is the same. Right? could be like polynomial functions, or it could be eigenfunctions or something. But two series will be equal if each term, corresponding term in the series is equal, right? So we need just to make an equality by elements of the sequence. It would be much easier if we would have the same index in the eigenspace. And no one forbids us to use different letters and start counting from different origin. Like, if we replace k minus 1 to m, it means that if you flip this minus 1 here, it means each k should be replaced by n plus 1. Right? So this one will become n plus 1, this one will become n plus 1, and this one will become. Summation of the same index. Is it permitted to remove summation? Let's vote. I vote for remove summation. Anyone with me? Anyone opposed? Anyone doesn't care? Okay. Thank you for sharing your. Yes, you do not care, or you?
So why is it summation from n instead of
We just replaced the index of summation with this.
so it doesn't have to change n plus 1, or it doesn't matter?
It doesn't matter. So if you remove summation, it will mean that two sequences on the left and right are equal when, and we also, not only the summation, we also need to remove the eigenstates. So whatever is here, mu times c sub n should be equal to n plus 1 c sub n plus 1, right? So under this condition, the two series will be if they equal element by element. This one must be equal to this one, because the rest is identical. On the left, the index is n plus 1, and the factor is square root of n plus 1. And on the right, index is n, and factor is mu, unknown eigen. No one can forbid us to divide both parts on factor. Right?
It just looks like complicated.
Okay.
So I just becoming familiar.
So if you divide left and right part by this factor, then what do you get? We get a connection of the senior term as a senior expansion coefficient in connection to junior expansion coefficient. What is the name for this connection between senior and junior? Everything we do is serious. It's not wrong, but there is more specific. Huh? Taylor is specific series for polynomials. And this, just generally, maybe not so much mathematically, but philosophically, one can make connection between generations, between different orders. Senior connects to junior, junior connects to series. It's a popular word and practice in computer science when a subroutine calls to itself. Huh? Well, it's everything is function, but there is more specific word. When a program calls itself, and then it means in time it calls itself and itself and itself. Right, recursion.
Oh.
Oh, yes. How nice that you know how to read. Okay, so basically the procedure to find exact values for any term in this progression is to find the root, the lowest order, and then apply this rule again and again several times and get terms of any order. Make sense? Not yet all of them. Very good. So, oh, it works. Very good. This is our plan, what we are doing. So we need to, I'm not going to throw you off and shock this new material. It's just repetition what we were discussing at the beginning of this meeting, just in the form of full chat. So we need to solve the time-independent Schrödinger equations through expansion, and we are getting to get observables, right? Like oscillating position, momentum, width, stuff like that. We are going to practice this eigenstate expansion, and we know eigenstates, we know eigenenergies oscillator, and we need to know this the expansion coefficients, which we almost know, right? They should reflect initial condition, and you are starting to see that for this specific problem, for oscillator, those initial conditions, those expansion coefficients will be algebraically due. And then we'll get here. So it's a non-linear flowchart. Oh, what's say here? Okay, and do you see the top line, or should I move camera? I don't know how to do it. Maybe? Okay, better. So this is the last slide. This is outcome of today's meeting. If we get to here, and I need to rush to get there, all goals will be accomplished. So the wave function will have some boring stuff in the front, summation over eigenstates, and the factors in front of eigenstate will oscillate according to this Euler stuff, whereas mu is eigenstate of the annihilation theory, eigenvalue of annihilation theory. So processing of this form, considering this phase accumulation multiplied by initial value, will give time-dependent eigenvalue of annihilation operator that oscillates this time. And in terms of this oscillating eigenvalue of annihilation operator, one will be able to find observables in a short. I didn't check, but if it was a real Nobel Prize award for this work in the 60s, but it was very close. So it's one of the precious accomplishments for all the kind. It's an analytical solution for Australia. What is interesting in this expansion? The number of eigenstates is placed in the denominator. Do you know this exclamation sign? it's like, N, how happy I am, right? Or is it something more? Which means, so it's typically a very big number. It grows like exponential or bigger. So the larger the number, the smaller the factor. So if we go to high index of the eigenstate, the factor will be vanished. So the series will converge for sure, no matter what we put in this thing. Right? And if you put oscillating stuff in the power n, and at each next power it will oscillate quicker, which is basically yes. What is Hermitian operator? Or just navigate, or just show. Top button. Top part of the circle, yes. It's harmonic oscillator.
Oh, okay.
Okay, so and I will rush to get to this slide as quick as I can. I know we are open fun club of my calligraphy, but I think I have it typed somewhere. Just wait. Yes, here. So if we here is our recursion rule. In expansion coefficient of the senior order is obtained from the lower order by u over square root of n plus 1. If we do know the lowest order coefficient, then we can find the coefficient number 1. Right? So we plug n equals 0 and u remains u. C1 equals u over square root of 1 times C0. No objections. Now, if we want to practice this rule once again for the next level, the coefficient C2 is obtained from C1 by mu in the denominator and square root of n plus 1, which is square root. But C1, to our knowledge, is mu over square root of 1 C0, which means that C2 is mu squared over square root of 1 times 2 over C0. So we do need only the knowledge of the lowest expansion coefficient C0, and then one can rule over this recursion procedure and get expansion coefficients of each one of those. Third, it's u over n plus 1 square root of 3, C2. And C2 is already known as mu squared over square root of 1 times 2, C0. And then we put it all together. We do the third power over square root of 1 times 2 times 3, C0. So 3 here, 3 there. 3 here, 3 there. So one gets to the higher order, then it's mu to the C sub n, mu to the eigenvalue of integration operator to the power n, square root of all natural numbers from 1 to n, times C0. Okay? Mu sub n, mu to the power n, or square root of n. Any expansion coefficient expressed in the zeros of the coefficient. How do we get the C0 coefficient? Do you consider ugly handwriting here as a prompt? So how do we get C0 coefficient? It's one number that we need to get, right? So the eigenvector of annihilation operator is composed with C sub n coefficient, and each C sub n coefficient is some factor times C naught. So C naught can be put out of brackets. What's that? Huh? First letter N? Yes. So if you want a good function, it should be normalized. So we take this eigenstate of annihilation operator as we found it, but we found everything except C naught and mu. If we plug in this eigenstate into normalization procedure, we should get one. And from this equation, we can solve for C naught. Okay. So if and now it's what Morgan. We need to use our strong experience in matrices and vectors and their multiplication. So if our wave function is in coordinate space, it is integral. But if it is representation in discrete space, then it is bra times ket is row vector by column vector. And C sub 1, sub 2, sub 3, those are our expansion coefficients that we just found on the previous slide. The same, just with stars. So we need to practice C1 star times C1 plus C2 star times C2 plus so forth. And this summation of expansion coefficients for this eigenstate operator should give 1. And since they all will depend on C naught, we can cancel something and solve for C naught. Oh, generous 10 minutes. We can do wonders. So here is what we are going to do. Multiply C sub n times C sub n with star, make summation, and make sure that it is equal to 1. It's not my handwriting. I think I was calling students from class to here. But we'll skip it because time is precious. So notice there are no eigenstates, no brackets. We just practice multiplication of coefficients. So this part is coefficient number n without star. C naught, n goes here and there. With star, we have C naught star, and we put star onto the mu. So who knows how to accomplish the summation? Any ideas? Or any skills in reading what is available on this side? Yes. Good. It's absolutely correct. And how do we what can we do with summation in the box? So we need to sum infinite number of terms, where in the numerator is basically mu squared times n, mu times mu in the power to n, and in the denominator is n factorial times n factorial square root. By the way, n factorial times n factorial square root will be what? Just right. So we do have a number which we can call x, just for purpose, to the power n divided by n factorial. X to the power n divided by n factorial. Huh? Yeah. Yes.
How to see the trend where it's going.
in your Calc 2, how many series did you practice in explicit form? All correct answers should be simple. Which functions do you were expanding into series? Huh? Exponential, maybe sine, cosine, and this. So, does it look like sine or cosine? What will be summation of that of if you have 1 plus x squared over square root of 2 plus x third to the not square root, 2 factorial, 3 factorial, x to the power n over n factorial. Huh? It will converge for sure because n factorial is very large. It will over 4 power any polynomial. I will draw in this little box. So if this is my x-axis, when x equals 0, it will be equal 1. Right? Then next term is linear. X. So it should go near 0, it should go linear. Next term x squared means if you ramp up quicker. Next term is x third, it means if you ramp up even quicker. Here it will be slower. So which function looks this way? Yes. So it is main take-home message from your talk. 1 plus x squared over 2 is a Taylor series for exponential. Right? And opposite, if you see 1 plus x squared over 2, it means it can be pulled back into exponential. So, what is this? This is mu star times mu is our x. In the denominator, we have n factorial. So it will be exponential of what? It's already written. So this red box is replaced by e to the power mu squared. Convincing? No argument? Okay, so now let's read the equation. 1 equals c star naught c naught times e to the power absolute value of mu. Can we solve it for c naught? If you assume that it is real, then it will be like we divide both parts by e to the power mu squared and take square root. And if you take square root, it will be just dividing power of exponential rate. This mechanism. So only this part is needed, right? We already agreed. If you solve for c naught, it will be e to the power minus mu square root. Next year, if you like both everything. So we achieved something. We know c naught. We know how to find any expansion coefficient of c naught. And if we plug it in, if you look on this equals, we'll put some normalization factor, but then it will be summation. Oh, we already know this normalization. It will be e to the power minus mu squared 2 summation. Square. Square. Please correct me if I'm wrong. I think it goes along with what we were doing. So this is C naught, and this comes from progression. Maybe there is no 2 here. So how do these coefficients behave? If n is very small, like 1, 2, then and mu is relatively large, then mu to the power n will be growing function. If n is very large, then doesn't matter what is the value of mu, it will be decreasing function. So if at the beginning it grows and then it decreases, there will be a maximum. So if you go from this summation is referred to so-called Poissonian distribution. It's a known series in math. It is already used in statistics. So there are processes that obey Gaussian distribution in average, and this is an alternative for a process that obey Poisson. Thank you for your patience, for commitment to the these materials, and look forward to see you at 5. Okay, it means you are not going to come at all, or which time you need to leave? Which time you want to leave?
Yeah, we like 5.
Sure. Oh, thanks so much.
I might be late for the I might be late for this. Like, I think I'm leaving by 6 because I got to do.
Oh, okay. Yeah, I'm happy for you. Yes.